let's do a little Q&A if you have any Qs. Go. All right, getting the presentation up now. All right. So last time we had talked about controls. We talked about electricity, voltage, current, and power. I assume that was all very basic review. Then we talked resistance, which again, this was just a definition of Ohm's law. I expect it was, again, basic review. Gets maybe got a little more interesting but again, this is physics, early physics. Just talking about resistance in terms of material properties. R equals the conductivity times the length over the area. I'm kind of emphasizing that because it's common between the different components. You end up with equations like this for each of the fundamental components, and they can inform you about how series and parallel connections work out if you understand it from a physical level this way. We talked about series and parallel connection of resistors, again, deriving these relationships directly from Ohm's law, and with the with the definition of the voltage and current in parallel and series. Capacitance we talked about again with this this fundamental capacitance relationship, charge over voltage, not being a terribly useful one that we see a lot every day, but the energy in the capacity is one that we do see often. And the discussion of reactance of a capacitor, of a reactive element. I don't have a good reason for you. I don't think I said this, but I don't have a good reason for you why this is the capacitor equation. There is one from physics. I just don't know it. I know an intuitive kind of way to describe it intuitively, but nothing more than that. So we'll stick with the equation for now. And how that transformed into the frequency domain, again, is sort of outside the scope. But the takeaway here was, again, the reactance of the capacitor equal to this 1 over j omega c. We talked a little about then just fabrication of capacitors, how it comes out. Again, the capacitance equation from physics shares that parallel with the resistance equation from physics, which I wrote there, handily enough. And again, can tell you a little bit about parallel connection of capacitors, where when you connect them in parallel, you effectively increase the area of the plates, thereby increasing the capacitance. When you connect them in series, the area of the plates is the same, but D increases, so you lower capacitance as you connect them in series. Again, so you can tell all that just from physics, not just the mnemonic that you got in EE 101. I don't know what it actually is at NC State. So then today we will talk about inductance. So inductance is the analog to capacitance. It's storing energy in response to a current, rather than a capacitor stores energy in response to the voltage applied to it. So an inductor does that with current instead. And maybe the important physical background of this is, if you remember back to physics, you have a current or any charged particle traveling, in a line in space. It generates a magnetic field encircling the axis of movement. this was the right hand rule where, oh God, I'm not going to draw a hand here. But if your hand was if your thumb was the arrow, the magnetic fields wrap around the wire as your fingers curl around your thumb. That's sort of, I would say clockwise, but it depends if you're looking at or away from the wire. Let's see, well, let me follow my script a little better here. So inductance is measured in henries. The fundamental units are, this Weber is a little hard to explain. Fundamentally, this inductance is a flux over a magnetic path length. I'll get into that a little more. I'll get into magnetic path length and flux. This is not a very useful equation from an engineer's point of view using an inductor. So we don't have to spend too much time on it. Oh, I'm sorry. This is over current. That's an I. Sorry. The inductance is the flux induced over the current applied. Anyway, still not a very useful equation. That's why I don't memorize it, and I make mistakes trying to teach you about it. So don't worry about it too much. A mechanical analogy to for inductance is that in a pipe or garden hose, you have water flowing. You turn on the spigot, water starts flowing. When you remove the pressure from the spigot, I won't say turn it off, but sort of like that. If you just stopped applying pressure to the hose, water would still flow in the hose just due to the inertia of the water. The water has mass. It's, a body in motion tends to stay in motion. That would be true for the water. That's the same for current in an inductor. So the current wants to keep flowing even in the absence of a driving force once it's in an inductor. So you can think of the property of an inductor being or the property of inductance being a component's resistance to changing its current. It wants to maintain the same current unless you are applying a force, meaning voltage, to change it. Let's talk a little bit more about this, this physics right-hand rule. So, okay, you have a wire, it develops a current, a magnetic field around it like this. That's not too useful. Now consider a wire where, I'm going to draw it like this. A wire going into the page is marked with this X. A wire coming out of the page is marked with the dot. So a wire going into the page develops a magnetic field like this. Oops. The wire coming out of the page develops a magnetic field like this. These circles should be more even. And they should look less like something. But here they are. So the point is the magnetic fields due to these wires reinforce in the center here. So if you do this a few more times, put another wire here, another wire here, you end up with a magnetic field that, oops, I don't want that color. Magnetic field that goes through all of them and sort of comes out the other end that way. And physically, the way you get this sort of arrangement is by taking a single wire and making a coil. So all I did here was cut down through the middle, and you see the wire, current is flowing into the page, out of the page, into the page, out of the page, into the page, out of the page. So that's how an inductor, it sort of concentrates the magnetic field due to a single current in this area. So we'll talk about that on the next page. Another definition thing that there's probably more physical background than I can understand right now. The energy stored in an inductor is equal to 1/2 the inductance times the square of the current in the inductor. This is analogous to the energy in the capacitor, which was 1/2 C V squared. So that's important. The inductors and capacitors are analogs in that way, and more that we'll see. Again, just like capacitors, they are ideally lossless energy storage devices. That you'd be able to store an infinite amount of energy in this magnetic field by passing, an infinite amount of current through the inductor. But in this case, we know that it's not lossless because we just made it out of a coil of wire, and we know a coil of wire has resistance, and therefore you put current through it and you get losses. So it's not ideal, but this is the ideal equation for that. All right, so we're talking about inductor. Like with the capacitor, I can't give you the total physical background of why this equation holds, but the meaning behind it is that if you have an inductor, that's what I forgot to do on the last page. And I forgot to give you the symbol. An inductor symbol is strongly, the circuit symbol is strongly influenced by this, coil construction. So that's the symbol for an inductor, which I'm sure you've all seen. Again, just like with a resistor, the voltage across the inductor and the current through it are defined this way. Let's make that a capital I because that's what it for us. In some European schematics, you will actually see a box, which is similar to a resistor, but this box is filled in. Don't know why they do it that way, but that's what you may see in some European schematics. You'll also see this, where somebody actually, curls the, but that's just an aesthetic thing. All right. So, again, so I was drawing one here. The physical, the sort of intuitive meaning of this is that you apply a voltage to an inductor. Let's say it's an ideal voltage source or a battery or something. So that's how we apply it. The voltage is directly proportional to the rate of change of current in the inductor. So if we look, voltage, we'll say we have a switch here, and we can apply, we turn the switch on at time t. So we apply the voltage across the inductor. The current in the inductor will rise linearly with the slope of the applied voltage over the inductance. When this voltage source is a sine wave instead, the current through the inductor, will, it will also be sinusoidal. it will be a negative cosine. Just imagine in your head that this is perfectly 90 degrees out of phase. You can see sort of the parallels here. When the voltage is high, the current is ramping up. When the voltage is zero, the current stops changing. When the voltage is negative, the current is falling. And this equation governs that whole thing. If you can do derivatives and integrals, you can work out, arbitrary inductor currents versus arbitrary inductor voltages. But those are the two interesting ones for us. Again, like with the capacitors, this differential equation can be transformed into the frequency domain and ends up looking like this. The V equals j omega L times I. Rearrange that into something that looks like resistance, and you get a reactance. So VL over IL in the frequency domain equals j omega L. Recall, let's see, did I do it? Yes. Recall that the capacitor reactance was 1 over j omega C, or negative j over omega C. So that's another way that inductors and capacitors are analogs of each other. That, instead of j omega L, it's 1 over j omega C. And since it's VL over IL, you can kind of imagine how, oh yeah, if you swapped voltage and current, it would kind of look the same. We'll talk about this. The signs of these reactances being opposite is important when we get to filters, which we'll, I think, hit in 2 slides here. Let's see. I stop here. Any questions on things I left out about inductors? Let's look at the last page. All right. Let you ask too much. Okay. Calculating inductance from a physical geometry is a little more complicated. Or maybe it's not more complicated, but there are many more ways to create an inductor than, say, a resistor or a capacitor. The resistor one was pretty straightforward. It's a block of material with a uniform cross-section, some length, some length and depth, whatever. Capacitor, we assumed it's a perfect parallel plate and some fixed distance between them. So for the inductors, we are assuming that, like I showed before, you have this coil. It has a length L, that is the L, small l in the denominator. There is an area that the coil encircles, and that could be a circle, it could be a square, it is an area. So that part's not too bad. N is the number of turns. So that all sums up, is the number of turns. N squared, that is not a term we were finding in our previous equations. There was no square term going on in resistors or capacitors. But this is sort of, this kind of informs you about that magnetic field concentrating effect I was talking about earlier. You have the same current flowing through this entire wire, but that it encircles the same area over and over again. That's what gives rise to this N squared term. When you have probably should have drawn this first, so I'll draw it again over here. If inside this inductor was a core, a magnetic core made of, could be iron or some other magnetic material, that is what gives rise, that is mu, the relative permeability of a of a material, and that you increase the relative permeability, you increase the inductance of the inductor. So an air core inductor like this has a relative permeability of 1. So it ends up being, the permeability of free space is like 4 pi times 10 to the minus something. Some, iron and steel have relative permeabilities of like 100 to thousands. Some of the core materials we use in the lab are like 10 to 20 relative permeability. This doesn't have to be a straight line. This can also be a toroid. With the turns wrapped around like that, all the way around. And then in that case, the L, the magnetic path length, is that. Still, the turns are just the number of turns, and the area is the cross-sectional area of that core. This could also be done as a square, and this could actually have even a third leg out here. Let's draw that just to make it interesting. These kind of shapes is where things get more interesting, because you can just wrap the turns around these inner legs here. But now the magnetic path length is all of this business. So this is why I was saying, oh, with this equation we're assuming this kind of geometry. And this equation applies to both this solenoid and toroid kind of winding. It does not apply so directly here. But I just want you to be aware that it happens, and the same sort of things affect the outcome of the inductance. The permeability of the core is still important. The number of turns is still important to that square power. The area, the cross-sectional area of each of these sections of legs is important, and how far the magnetic field path, or the magnetic path length is, all affect the inductance in kind of the same way, just in different proportions when you get to the core, or it's rather more, more complicated to calculate an effective area and path length. So, okay, so that's some ways of constructing. Oh, well, whoops. So toroids, that's this guy. The rectangular inductors are these guys. Parasitic inductance. I kind of hinted at it earlier that when you have a wire, it generates the magnetic field around it. Well, it's kind of like a one-term inductor. There's another equation to define the inductance of that one-term wire. But in a lot of cases, you're going to have, say, this is a 120 volt line. You have the line and the neutral. Current comes back. You usually send current out on one wire, and then current comes back on the other wire. Well, this guy generates a magnetic field too. And there you see between them, the magnetic fields interact, and they create basically a one-turn inductor. Except the area enclosed by the inductor is all of this business. The the length is very short because it's just, into the page here, the thickness of the wire. The permeability is probably mu, just the permeability of free space. And n is 1. So you see with wires, the parasitic inductance you get is really very strongly related to the area enclosed by the wires. So running your cables like this versus running your cables like this, where they're zip tied together every foot or so, running your cables like this is a much smaller inductance than running them, a few feet apart. And that can affect our circuits pretty significantly if that's done, if you have wires running feet apart for hundreds of feet across the lab. It's going to amount to a significant inductance. It's also a great way to pick up noise, because just like wires spread apart can generate a pretty nasty magnetic field between them, they're also sensitive to magnetic fields passing between them. So if you do this with your signal cable running over, say this was your signal cable and you put a power cable running right next to them. Now the magnetic field of the power cable, which may be pretty high intensity or high frequency, is coupling right into your signal cables and then can be generating noise. So a lot of reasons to keep both your power and signal routing tight. There can be a lot more to be said about inductors and how to make them, but maybe it's not too useful right now as a basic thing. The takeaways from inductor, the discussion about inductors. The energy can be somewhat important when you start designing, if you were to be designing inductors from the ground up, it's a design method using the energy stored in an inductor, but it's not a quantity we'll use day to day in dealing with power converters. The differential equation governing voltage and current in an inductor is far more important and would be used day to day. The reactance of an inductor is incredibly important and would be used. The relationship of permeability and number of turns and area and all that is important to keep in your head as just something to have an intuitive feel for. You put more, because you might do it in the lab one day. Just say, oh, I wish I had more inductance. I want it to be double. If you think about this equation, if you double the number of turns, you're going to get 4 times the inductance. So you're not going to do that. Or if you were dealing with, it's going to be very rare where you're dealing with air core inductors and you're playing with area enclosed by the winding. So that's important. Just this n squared. If you want to double the inductance, you put on 40% more turns. It's the square root of 2, 1.414. That's probably the important thing to take away from this slide.
Like the Nidecon inductor, would that fall in the rectangular type?
That would fall in the rectangular type, yeah. And the Nidecon inductors get a little more interesting because they will have actually windings on all 3 of these legs. Some of them, like the Atlas Copco ones, I think are 3-phase inductors. They've got winding on all 3 of these. And that gets interesting because the flux induced, the magnetic field induced in the core is different for each of the 3 phases. And it opposes, and I actually don't totally understand what effect that has on inductance. Basically, those inductors share some similarities to transformers, but it's a little too much for today because I don't totally understand it, so I'm going to skip it. But there are some single-phase Nidecon inductors that do just do, you know, they'll be, and some of the ones we have in Acme too, you'll see them out in the lab. They'll have turns on both legs, and maybe those will be connected in series. So that just kind of makes it look a little more like a toroid. Windings connected in series on the same core is the very same thing as just putting more turns on the core. That just reminded me. Another thing you can think about here, I mentioned before how you can work out the series and parallel combination of resistors and capacitors from this physical equation. You can do it for inductors as well. It's a little less obvious. Let's take two inductors connected in series. Well, they each have a length L and a number of turns N, and the area is the same, and they're both air cores, so same permeability. So you consider you'll have one inductance with mu n squared A over L, and the second with the same. If you consider these as the same inductor, what you would end up with is, so let's say, you would end up with 2n squared, mu is still there. The area would be the same. And you would get twice the length. So that would come out to mu 4 n squared A over 2L. You can imagine how 4 and 2 would cancel out to just give you 2 mu n squared A over L. So by connecting these two inductors in series, you got twice the inductance of just one. You can do a similar thing with parallel. It's a little easier because you just double the A. You double the area when you put them in parallel. The lengths stay the same, the number of turns stay the same. It's a little bit of gymnastics to make that work. Actually, I'm sorry. Inductance in parallel. Forget what I said. I don't know how to do inductance in parallel in this equation. Because it's a little more involved than just putting them nearby. I'll figure that out another day for you guys. So all of this was leading up to a discussion of sort of frequency response and filters. So before we said, okay, resistance is a voltage over current. Reactances are sort of AC, voltage over current, and for an inductor, it's J omega L. For a capacitor, it's negative J over omega C. So let's look at some basic filter circuits and use these reactances to sort of inform what they do. So the first and most common in electronics is an RC filter, like this. Input voltage, and you might be looking at, say, an output voltage here. If we take the, and then this has a resistance R and a reactance X over C. We know that from the capacitor reactance, omega is frequency. When you set omega equal to 0, which is DC, this equation blows up to infinity. So it's an infinite reactant. It appears to be an infinite resistance at DC. So you could rewrite this circuit as R, and then it's just connected to an open circuit because it's an infinite resistance. So in that case, it's just kind of a pass-through. V out equals V in. All right, well, let's consider then high frequency. When let's say omega approaching infinity. In that case, you get negative J over 0 times C. Well, sorry, over infinity times C. A number over infinity is, in math terms, undefined, but I don't care. I say a number over infinity equals 0. So at high frequencies, this circuit will start to look like a resistor and a short circuit. So V in and V out. So V out always equals 0 at high frequencies. Doesn't matter what V in is. At intermediate frequencies, what you'll end up with is something in between. I'm not going to do out all the equations for that. I just want to try to help you get the intuitive understanding of this is a low pass filter. At low frequencies, the output equals the input. At high frequencies, the output is 0. If you put this on a Bode plot, which is a measure of amplitude of V out over V in versus frequency, which again, omega is 2 pi f. So omega is in radians per second, f is hertz. The Bode plot of the low-pass filter, is flat for a while. Of this RC low-pass filter is flat, and then tends towards 0 at high frequencies. And this is known as the corner frequency. So, sorry, this is going to be omega c. Corner or cutoff frequency. And that where that is defined by the values of R and C. Again, not going to go through the derivation, just want to introduce the concept. If we replace the capacitor with an inductor, we can go through a similar exercise and say x of L at omega equals 0, x of L at omega equals infinity will give us, remember, j omega L. So at DC, that is 0. It's a short circuit at DC. At infinity, the L stays constant. Omega went to 0. At infinity, you get J infinity L. Infinity times a number is infinity. So at high frequencies, the inductor looks like an open circuit. And at low frequencies, it looks like a short circuit. So just by analog to this discussion up here, this ends up being a high-pass filter, where the output voltage comes through sort of unharmed at high frequencies and is attenuated at low frequencies. And if now, I didn't leave myself much space for it, but in power converters, we will combine the two. We won't use a resistance in the output of our power converter because that's a loss. Remember, inductors and capacitors are ideally lossless elements. So if we use them together this way, L in series, capacitor sort of returning. What we get at low frequencies, the inductor is essentially a short circuit. And at low frequencies, the capacitor is essentially an open circuit. So you just end up with total pass-through at low frequencies. No resistance like we see here. So V out equals V in, even if there's current flowing to a load out here. At high frequencies, the inductor is infinite resistance, and the capacitor is a short circuit. So you end up with a circuit like this. So V out is still zero because no voltage from the input can get to it, and it's shorted out by the capacitor anyway at high frequencies. Where it gets interesting is if, so V in equals the voltage over the inductor plus the voltage over the capacitor. Which, what am I trying to say here? And the current through them is the same, right? Because they're in series with each other. So this comes out to the input voltage equals, thank you, J omega L times I plus, rather, minus J over omega C times I. Let me erase so that it's a little easier to see. Minus. This is kind of what I'm getting at here, is this J omega L minus J over omega C is the effective resistance of this circuit at a particular frequency. What can happen is at one particular frequency, the term omega L exactly equals 1 over omega C. So that when you subtract a number from that same number, you get 0. And that results in resonance. Let's see if I can draw out how this ends up happening. So we said the low frequency function of this is to pass. The high frequency is to attenuate. And then at this corner frequency where the omega L equals, minus, or omega L equals 1 over omega C, you get this resonance. So the output voltage is actually amplified at this particular frequency. I could have picked a better bit of math to go through this, but this is kind of what happened. Trying to give you a good way to think about that. See, let me give myself another slide. Let's look at our L and our C. So this is J omega L minus J over omega C. So V in and I, so the input voltage is applied to the circuit. I goes through both the inductor and the capacitor. These reactances add when they're put in series, so that's what gave us the j omega L minus j over omega C. So that is the effective the effective resistance, or the equivalent resistance of this circuit at a frequency. I'm giving the letter Z here stands for impedance. Don't worry about that too much. It's just it's going to be like an R. It's going to be like resistance as we do this equation. So that's the effective resistance of this circuit. So V, we know from Ohm's law, V equals IR. Reorganize there. So V in over the equivalent impedance gives you the current. And we said V out is this. V out equals that same current times the impedance of the capacitor, which is that J omega C. Let's substitute in. We have I defined by this, so that gives us V in over J omega L minus J omega C times minus J omega C. So that's what V out is. So what I was getting at before is when omega L equals 1 over omega C, this goes to 0. Any number over 0 goes to infinity. So it doesn't matter what V in was, doesn't matter what the particular impedance of the capacitor was. When this condition is met, omega L equals 1 over omega C, this goes to infinity. And that, I hope, explains the corner frequency, the resonance at the corner frequency that we were showing before. I didn't explain why this happens at the corner frequency, or why the two are related, but I just wanted you to be aware that that happens. The important thing about that resonance also is that if I solve for I, remember that was V in over 0 now at that particular frequency, I goes to infinity as well. So it's not just that the magnitude of the voltage appearing at the output goes to infinity, the current drawn from the source goes to infinity. This is where parasitic resistances in the circuit actually help us. The parasitic resistance of wire and the inductor and the capacitor all limit this to something less than infinity. But it still can be pretty high and cause us problems. And it appears in control design. It appears in loss analysis of multiple parallel converters. So, being kind of comfortable with this way of dealing with reactances is helpful. So that's probably 4 weeks of introductory circuits in an hour. Let's see. What questions do you have? Or maybe, let me try this. Everyone tell me one thing you understand now that you didn't before. And we'll see. We'll just go from there. Kyle, what do you got?
Well, I didn't think about this resonant. I took most away from the conductors, the physical properties of conductors.
Okay,
coil,
the turns and
the more than the actual coils inside.
Yeah.
Or like that, fundamentally, it's a lot about how the coil actually turns.
Yeah, so there's a lot in the geometry of inductors. How about you, Chris?
Yeah, sort of about that. I have a question was,
On the inductors?
yeah,
Okay, scroll back here.
but also the frequency, like, what's the intuitive explanation of why at high frequencies inductor impedance goes to infinity?
Because, okay, so if we look here at the sine wave, you can sort of think of it sort of, what's the area under this curve. At DC, that area is a lot, so it gives you a lot of time to ramp up the current. At high frequencies, it's a very small area, so it doesn't give the inductor current much time to rise and similarly fall. It's symmetric, but it ends up just being small deviations around zero for the inductor current. So thinking back to the definition of kind of impedance is voltage over current with a small. When the current is small, the impedance is very large.
And then physically, that's
Physically, I don't know I can't explain well the background, but for some reason, to get a magnetic field established, it resists changes in the magnetic field, and that manifests in a circuit by resisting a change in current. That's about all I can say from that physics perspective. Will?
I don't really have any huge questions, but I really hadn't heard any of the corner frequencies before, so that was.
Okay. Yeah, and we can, let's see, I'm trying to think of if there's more relevant stuff to talk about here. Maybe we can make it a point in a future session to actually go into the math behind, well, how do you figure out what the corner frequency is? Because I can tell you that the corner frequency for this circuit is 1 over the square root of LC. I can tell you that, but we can also derive it from the equations. So basically what we were doing here, if you rearrange this enough, this will sort of fall out.
you have it right down there. Omega L equals 1 over omega C.
It does sort of come out that way. Let's see what time it is. I don't have enough time to go over it now, but yeah, it does sort of come out in that way. There ends up being a polynomial term in the denominator, and one of them happens to be. And there's also some definition. The corner frequency is defined as well, in an RC circuit, it's defined as where you've lost 3 decimals of gain. This deserves a whole topic in it. So anyway, the corner frequency of this circuit is 1 over the square root of 1 over the square root of LC. In an RL low-pass filter, that corner frequency is 1 over RC. And that's where you'll hear RC time constant every once in a while. That also is sort of defined as tau, time constant.
So in terms of like what we're using this for, we're essentially designing the circuit to change your voltage based on reaching some point near this cutoff frequency or this corner frequency.
Yeah,
not
you're
necessarily going infinite.
Yeah, you're typically interested, when you do this circuit, you're typically interested in, attenuating some high frequency content in a particular signal. The drawback, I guess, maybe I can make this point a little clearer. One of the reasons you would use I think I said already, oh, well, if you do an RC filter, you always have to pass current through this R and generate losses. So we went to the LC filter to avoid those losses. The LC filter introduced resonance, which is a problem. It can be, you can use it to your advantage, but it is a problem that the RC low-pass filter doesn't have. You don't have any of that nonsense. So it's getting you the lossless nature of an LC filter brings the problem of the resonance. But generally, why you put this filter there to begin with is to attenuate high frequency signals. And there are arrangements. Like I said, there are high pass filters that you can create. There are higher order filters, like if you have more elements, you can create notch filters that selectively attenuate a particular frequency. And you can create band pass filters, which only pass signals in a certain frequency band. So it's basically a low pass and a high pass filter together. It gets rid of low frequencies and it gets rid of high frequencies and it leaves you medium frequencies. And how resonance impacts all those circuits can be important as well. All right, Renee.
I have a little bit of questions about, like I understand the resonance concept and everything, but like I'm more curious about like more of the control of that and where we're going with, this infinite spike and what intuitively do we want to do to this or our power electronics or in general.
Yeah, from a control perspective, and I won't get into how we accomplish it, but like I said earlier, the parasitic resistances of the L and the C make this go to less than infinity. So if I were to draw that out a little more cleanly, maybe I can draw straight lines this time. If there were little parasitic resistances in here, instead of going to infinity, this resonant peak might go like that. So it still goes above, say, the passband, but doesn't go to infinity. What you can do with clever VSP control or even analog control of anything is that you can make the circuit think that you can put in a virtual resistance to the circuit by feeding like the current of the system back, and you can essentially modulate the voltage to make it look like there is a resistance. The circuit, you don't pay any losses in the circuit due to that virtual resistance, but you can add it in as a control, and it will have the same effect of limiting the peak of the resonance as a real resistor would. Subject to limitations of bandwidth of the control circuit, sample rate and all that.
What are kind of like the implications of having too large of a spike, or like what can go wrong with
too large of a spike, and this
clearly we'll have like more current.
Yeah, you're right. Besides the more current thing, we'll say the current is limited by the parasitic resistance. The problem can be that with very little, input, you can have just like a white noise input of voltage here, and since the gain to that white noise is uniform in frequency distribution. So at some point, that white noise will excite this resonance and give you output when you didn't expect it. And in terms of controlled circuits as well, and this gets into linear systems theory that we haven't gotten there yet, sort of spurious response to noise can lead to unstable systems because it's reacting to itself, and then you know, phase shifts due to the L's and C's, like, you know, this phase shift of voltage versus current, and the similar phase shift we get in capacitors of voltage versus current, can cause instability where the control loop sees you know, it sees like the positive side of a sine wave and decides, oh good, I should give it some more positive sine wave. And it becomes this feedback issue which causes the circuit to go unstable. So it's a stability issue as well as, well, I guess that is it. It is a stability issue. It's a, you know, it can create nonsense out of noise.
Are there any questions that I would say that definitely the resonance part is the most interesting thing. We have probably seen one of those before.
Yeah.
That was something I didn't really recall very well.
Gotcha. Yeah, just trying to build up the base that would make a little bit of sense. Yeah.
I think just the different types of variations of factors really can kind of get creative.
Yeah, yeah. There's definitely a lot of different ways of constructing. You know, you can some other interesting ones that we may not necessarily use here are one of them is a spiral inductor, where one wire comes in and it's just wound flat like this. You'll actually see these in wireless charging because, you know, the geometry is, you know, very nice to put on a table. What's interesting about this one is that the area enclosed by each turn is different as it spirals out. So this equation really doesn't apply when you're talking about spiral inductors. There's the inductance of coaxial cables. Coaxial cables have if you cut them open lengthwise, they have a wire in the middle. This is like, you know, TV cable. They have a wire going in the middle, and it's a bad way to show it. The return wire, you know, I was showing like two discrete wires over here. For a coaxial cable, the signal comes down on the inside and it returns on the outside. So that's a different inductance. You know, that's, you know, the area is still sort of the distance between the wires, but it's around an entire cable. And this also has a lot of capacitance. That's another thing here. A lot of these constructions of inductors can give rise to capacitance because you're taking a bunch of wires and putting them near each other. So now you have wires that are near each other with some insulation between them. You end up with a little bit of capacitance between each turn. With the Nidecon inductors, that effect can get very profound because the Nidecon inductors are plates. The windings are made out of the plates, and that ends up looking, starts to look like this parallel plate capacitor. A lot of overlapping area, and, you know, and a voltage applied between them gives you a capacitance. So then you have components that don't look like doesn't look like an inductor at all frequencies. It might look like an inductor at low frequencies, but at high frequencies, the capacitor starts to take over. Similarly, wire-wound resistors. I talked about them back here. You take a piece of wire, spin it up in a coil to look like a resistor, and surprise, you got some inductance, even though you didn't mean for it to happen. And these are all things that once you understand how they can happen in a way you didn't intend, you can counteract them. Wire-wound resistors in particular, they'll wind the wire one way, and then at the end, they'll turn back on themselves, almost negating the magnetic field created by the turns going, the magnetic field created by the turns going one way gets negated by the magnetic field of the turns going the other way. And that way they reduce the inductance of what should be an ideal resistance. So all this stuff sort of happens. It does happen a little bit with this type of capacitor where it's sort of wound up. You do get some inductance in that. I don't know how they deal with it, honestly. I just know it happens. So, every component, you would like to think it's just an ideal resistor, inductor, or capacitor, but they're always going to have a little bit of the other types of components in. Everyone will have a little bit of capacitance sometimes just because they're, parts, conductive things near each other. Everyone's going to have a little bit of inductance just because there are leads. And like we said before, a wire has a certain amount of inductance. This area enclosed by the leads connecting to a PCB, a little bit of inductance. And everything is resistive because nothing is perfect in this world. So that is probably enough for today. Originally I wrote down that, this is still accurate, that session 2 would be kind of introduction to switching power. So switch mode power supplies is what we work in. But I wanted to have the background of basically LC filters before we got into that, for why we make some certain decisions about how we deal with power converters. I'll sort of split this in two right here, where we'll talk about ideal converters, and then we'll talk a little bit about non-ideal devices. I don't think this is generally interesting to everyone, but it might give people a little bit of background about why we work with certain technology, like silicon carbide. Why does anyone care about that? That would be answered right here. After that, I'm thinking we need to talk about AC power, single phase, three phase. This is where I talk a bit about transformers, because that's where we start to care a little more. Energy storage, and then we start getting into maybe some advanced topics where the sessions really would be multiple sessions. But that's kind of what I think. We can always change up the lesson plan as we go. So with that, let's stop there, and I will stop the recording. Thank you guys very much.
Thank you.
Yeah, this is great.
And Tuesday, right, or Thursday, I said, was the next one. So I will make a presentation between now